we talked about, let's see, what did we talk about? Singular value decomposition, one of the most useful things around. You did some homework for today. Some people made some interesting comments about the proof by induction to prove the existence of the singular value decomposition. I would suggest looking at it on Piazza. It turns out that the proof by induction that I give there almost works as is for the case where m is less than n, but there's this slight subtlety where in the recursion you may end up running out of rows if you don't have more rows than columns. And then of course you have an option of either fixing that proof so that it's general or doing the proof for m greater than n separate from the proof where m is less than n. And strategically, what I like to do is have a proof for one case and then make it a homework to do a proof just like it in order to sort of force you to go through the proof that I did so that you understand it carefully. And that's really the strategy there. Obviously, you can also prove the case where m is less than or equal to n by simply taking the transpose. Okay, and that works too. Anyway, are there any questions about the homework or the material we went over in the last lectures? We're good? Okay, so now the problem is that I think so far we have yet to see a practical algorithm. Okay, we saw an algorithm for constructing the singular value decomposition, but there are all kinds of parts and pieces missing in that algorithm. And what we're going to talk about today actually is a practical algorithm you've seen before in, say, an undergraduate class for this. It's the Gram-Schmidt process for taking a bunch of vectors and making these vectors mutually orthonormal. Except the algorithm is not practical. Okay? So it's practical from a mathematical point of view, but we're going to see that there are some subtleties there where if you incur round-off error as you do your computation, the Gram-Schmidt process may actually give you a set of mutually orthonormal vectors that are anything but mutually orthonormal. And since the whole purpose is to find mutually orthonormal vectors, that's a little disquieting. I had meant to show you an animation that I created for my undergraduate class, and didn't quite get around to pulling it together because unfortunately I have to put a whole bunch of different files together in order to do it. But if you go to this undergraduate text that I created for this massive open online course last spring that Maggie and I created, if you go to section, I think it's 11.3.3, and you go through some of the videos, you'll actually see the animations there. And this gives you a 3D feel for what's happening in the Gram-Schmidt process. Okay? So if you're having trouble visualizing the Gram-Schmidt process, then I would recommend doing this. If, on the other hand, you're perfectly okay with it, then you don't need to. All right? So the progression is we're going to look at the Gram-Schmidt process. We're then going to give a slight modification of the Gram-Schmidt process that's known as the modified Gram-Schmidt algorithm. We're then going to sort of demonstrate that you can come up with matrices where one of the algorithms, the classical Gram-Schmidt one, fails miserably. Modified Gram-Schmidt does better, but still leaves something to be desired. And that then leads to a much more practical algorithm that's used all the time. That's, from a practical point of view, one of the most important results in this class, and that is the householder transformation-based QR factorization, and that will come in Thursday's lecture. And householder transforms, also known as reflectors, are one of the most important tools that you bring to the table in numerical linear algebra. So it's a very important topic, very practical. Okay, so let's get started on the Gram-Schmidt process. Thank you for, where are you? The notes. Somebody was organized and printed them out. And actually, well, let's have a look. How does the Gram-Schmidt process work? Probably need to start bringing pens because I think we're down to only a black pen. Let's hope it works. So the idea is as follows. When you're talking about 3D, and obviously when you take lots of physics classes, etc., 3 dimensions is really important. The natural basis in which you work are the unit basis vectors, right? In physics, you would call them, well, we may be in trouble. The red pen does not work. Good. You have the basis vectors I hat, or I vec, j vec, and k vec is what they're often called. And these are the vectors in the various directions, right? Now, when you took a physics course, you may have run into situations where it was convenient to use a rotated system instead. And, but still orthogonal. Why is orthogonal nice? Because then by just projecting onto the various axes, you can figure out what the coordinates are in that coordinate system. Now, it's often the case that you start with a bunch of vectors, say 3, and they kind of point in different directions, which obviously I'm having trouble drawing here, which is why in the animations that I have, I actually rotate a 3-dimensional view of this so you can see what's going on. And notice that any time you do something like A times X, if you have 3 columns in A, you end up with the 3 vectors. So in some sense, you're expressing this vector that is the result of doing A times X as a linear combination of those columns of A. But these vectors are not necessarily mutually orthonormal. Hopefully they are linearly independent, so that you can actually have at least a unique way of writing a vector in terms of these columns of A. So it's very often the case that what you would like to do is to take these vectors and make them mutually orthonormal to create a nice basis for the space that you can get by taking linear combinations of those columns. Okay? So at that point, the problem becomes, given a bunch of vectors, A0 through AN-1, find Q0 through Qn-1 such that, number 1, the span of these vectors is the same. And number 2, the vectors are mutually orthonormal. Orthonormal vectors we've seen. Yes?
Are you necessarily finding the same number of vectors?
Yes. You're typically interested.
You're assuming they're all linearly independent?
So we will start with linearly independent. Very good. When I don't look at my notes, I forget things. So point these out, please. Thank you. All right? So that's the purpose of the game. Now, if you only have one vector, and you would like to create, notice that the space spanned by that one vector are all multiples of that vector, right? So it could be negative. There we go. Right? All of those vectors. And if we want an orthonormal basis for that, all we really need to do is take that vector, make it of length 1, and we're done. So if we only have one vector, all you need to do is compute the length of that vector, and then create a vector that has length 1, and you're done. So that's easy. So that's the first step in the Gram-Schmidt process. You take the first vector, you make it of length 1. Now I'm doing this purposely through 2 steps because it's going to turn out that this value is important. Yes?
What's to stop you from just returning the trivial answer of all the unit basis vectors?
Okay. Well, because if this were 4-dimensional space, so certainly if you only have one vector.
Take the unit basis vectors in 4 space then. I mean, it's bands.
Okay, but if you only have one vector to start out with, and you want to find a orthonormal basis for the space spanned by that,
I see.
the unit basis vector won't work. So typically you have fewer vectors than you have rows in the vector, or elements in the vector. Okay? Now, I'm going to go, as usual, through the material slightly differently so that you get multiple perspectives, and sometimes, in person this is easier to do. So I'm going to go over here, and I'm going to give an interpretation of this. And the interpretation of that over there is that A0 as a column of a matrix is just Q0 as a column of the matrix times row 0, 0. Okay? And that's just by virtue of the fact that we computed Q0 from A0 by dividing by row 0, 0. These two are equivalent, right? Now, anytime you have 2 vectors, you can always think of the plane defined by those 2 vectors. And you can always take that and you can walk onto the whiteboard, right? So we can say, look, we started with A0. We computed from that Q0. If we now have a second vector, let's make it A1. Then we've taken the plane defined by the linear combinations of those vectors and we've plopped it onto our whiteboard. And if you now want to come up with a vector, sort of eyeballing this, what do you really want? Well, I really wish I had more color. But what you would like, just sort of eyeballing it, is a vector that points in this direction that's orthogonal, right? Now, how do you find that? Well, you can say, look, this vector you can think of as the vector in the direction of Q0 plus the vector orthogonal to it. So let's call this A1 perpendicular. Okay? And what do we notice? Well, we notice that A1 is equal to some constant. Let's call it constant rho, comma 1 times Q0 plus the vector that's orthogonal to that. Okay? Now, the problem here is we have one equation and we have 2 unknowns. We'd like to determine this and we'd like to determine that. But what we know is that Q0 is orthogonal to that right there. So what we can do is we can say, well, Q0 Hermitian times A1 is equal to, and I'm just going to take a few shortcuts, this right here, because we can always bring a constant outside, plus Q0 Hermitian A1 perpendicular. But what do we know? We know that this here is of length 1, this here is 0, and we've just come up with a formula for row 0, 1. Okay? So we have a process by which we can come up with the perpendicular vector That gives us this vector. But then a vector in that direction of length 1 is simply that vector divided by its length. So what we do is we say let rho 1, 1 be equal to the length of A1. And then let's let Q1 be A1 perpendicular divided by its length. So far, so good? Who has seen this before in some class? Oh, come on. Everybody's seen this in some class. Physics class, math class, okay? It's the Gram-Schmidt orthogonalization. I suspect they crammed it down your throat in high school without telling you what it really did, but here's the algorithm executed. Or maybe not, all right? Maybe they just don't teach much anyway. So, but the important thing here is that if you look at this right here, you can write, well, you can write now that A1 is actually equal to rho 0, 1 times Q0 plus rho 1, 1 times Q1, because our A1 perpendicular was equal to rho 1, 1 times Q1. You see that? And that you can write as the vectors Q0, Q1 times the coefficients rho 0, 1, rho 1, 1. Okay? And that you can take up here. Let me rewrite this slightly. Now, why is that? The second column here is this times that plus this times that. Okay? Well, what does that mean about this entry? Better set it to 0, right? So there's a relationship between A, Q, and these values rho starting to emerge here. Okay. Let's do one more. What if we now take this to be the span of Q0, Q1? Okay. And now we're given a new vector. What would we like to do? We would like to create from this vector an orthogonal component. And then from that orthogonal component, we would like to create a vector of length 1 in that direction. So we want to create this picture right here. Okay. Now, what do you know? You know that A2, if we're going to create a vector Q2 of length 1 here, then what we want is we want A2 to be some multiple of Q0 plus some multiple of Q1 plus some multiple of Q2. Right? We need to determine what these various things are. Well, we can look at Q0 Hermitian A2. That's equal to rho 0, 2 Q0 Hermitian Q0 plus rho 1, 2 Q0 Hermitian Q1 plus rho 2, 2 Q Hermitian 0 Q2. This is equal to 1. This is equal to 0. This is equal to 0 by design. And what you find is that we have a formula for computing the coefficient for the component in the direction of Q0. Similarly, you can argue that Q1 Hermitian A2 is rho 1, 2 times period. Okay, that's replacing a 1 here, 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 and here, recognizing that that wipes this out, leaves this alone, and wipes that out. So we can compute that. Then we can form, that tells us the components in this direction, in the span of Q0 and Q1. We can then compute the component orthogonal to that by subtracting those components out. And then we're left with computing its length. And forming a vector that is of length 1 by taking the perpendicular part and dividing it as its length. You with me? This, right here, we can express here by adding A2 as another component, Q2 as another column. And those coefficients into our matrix right there. Okay? So what I'm trying to show here is that this Gram-Schmidt process that you may or may not have seen before is actually equivalent to computing a factorization of A. Here is matrix A that has these vectors as its columns. We often like to take collections of vectors, cram them into a matrix, and make them the columns of a matrix. This is a matrix Q. And this is a matrix R. And what do we know about Q and R? We know that Q has mutually orthonormal columns. That's how we express that. You did homework for that for today. And R is upper triangular. And there's actually one more special thing about the diagonal elements of R, and that is that they are real and positive. Okay? Why are they real and positive? Well, they equal lengths of vectors, so they must be real and positive. And if the matrix A started with linearly independent columns, then you know that every time you subtract out components in the other directions, you're always left with something, because otherwise it's not linearly independent. And therefore, you know that it has length, and therefore you know that the diagonal elements are positive. So this is known as the QR decomposition of matrix A. It actually exists if the columns are linearly dependent as well, but let's not go into that little detail. Okay? It always exists. There's always a QR factorization of a matrix. Very, very important thing. What we're going to see in the next lecture is that QR decomposition, the singular value decomposition, can both be used to solve the linear least squares problem, which is yet another really important problem in linear algebra. Okay? Any questions about this? Well, we've done it for a matrix with 3 columns. Hopefully, you're good at seeing patterns, and you've seen what the pattern is here, right? So you can extend this to matrices with more columns. Let's see how we might be able to express this. And for this, I'm going to just call up the screen because otherwise, let's see, I don't want that. I've got so much stuff on my computer. I often can't remember where is what. I think this is here. My computer is really not in good shape today. What is going on? Must be Microsoft, right? I shouldn't say that on video. Papers, notes, Gram-Schmidt. I think I just have too many applications open or something. I don't know. I try not. I mean, if things really go wrong, I hand it to a student and say, fix it. Okay. What in the world is this? Okay. So in the notes, I go over this. Let's see, can we see this? And what essentially I have in the notes is exactly what I just described. Okay? So I should have just said go read the notes, and then you could have done something useful in this class. In the notes, I also give 3 equivalent algorithms. Actually, I give 4, 5, 6, maybe 10. I don't know. One of the things that I like to do when I explain things is I like to explain the same thing from multiple angles in the hopes that for each of you I hit on one of the angles that actually works for you. Okay? And then I try to tie them together so that if you only really get it when we put the spotlight on from one side, hopefully by now understanding it from that side you can then relate it to the other spotlights I put on the same subject, and then you can learn to think about the same problem in multiple ways, which is always important. So what do we have here? Actually, in the middle, we have exactly the algorithm that I just described. Okay. What happens every time you're given a new column, AJ, you compute the coefficients for the components in the directions of the previous orthonormal vectors that you've computed already, 0 through j minus 1. Once you do that, you set AJ perpendicular to AJ, and then you start subtracting off components in the other directions, leaving you with the perpendicular part. That's the loop, the second loop in the body of the outer loop. And then once you're done subtracting out components in the different directions, you compute the length, and you normalize the vector to have length 1, and you're done. So far, so good. On the left, we have a slight modification of that, where in the same loop in which you compute that coefficient, you also then go ahead and subtract it out. Obviously, that's the same thing. Right? And then on the right is a formulation that kind of banks off of what I tried to put up there, explaining where the upper triangular matrix comes from. And let's just relate that to the algorithm in the middle here. Okay, what do we have? That loop that you do up on top there really computes all of the entries in the current column of the matrix R. So over here, I'll turn the light back on. If J is equal to 2, then you can partition this as such. And what really is going on is that you're computing all of these values right here. But instead of computing them in a loop one by one, you recognize that you can think of them as a vector that needs to be computed. It's part of a column of the matrix R. the formula for each of the individual entries is now given by, the appropriate column of Q transpose times the vector AJ. And then you guys have learned how to do slicing and dicing and all that of matrices. Notice that what I should have said was that Q0 Hermitian AJ through Q0, so Qj minus 1 Hermitian AJ is equal to the matrix that has as its rows Q0 Hermitian through Qj minus 1 Hermitian times the vector AJ. Remember, when you do matrix vector multiplication, you can think of that as dot product. And then that can be thought of as the matrix Q0 through Qj minus 1 transposed, Hermitian transposed, times the vector AJ. Okay. And as a result, you can formulate the whole thing as one matrix vector multiply instead of having to think about all of these individual loops. I don't like thinking about individual loops. One thing that you're going to find out is that almost, I think, every algorithm we run into in this course, I can reformulate as a single loop around other operations. Okay? Here we have a single loop around what operation? The first loop that was there, I reformulated as a matrix vector multiply with a transposed matrix. And then if you look at the second loop there, I actually reformulated that as a matrix vector multiply as well. Okay. And then once you're done with that, you compute the length and you normalize. Kind of interesting. Yes?
Why is AJ?
Why is it AJJ? I think that's a typo. That looks suspiciously like a typo. It almost looks like it's something that went wrong in converting it into. I'll have to check. Yeah. Let's blame it on the projector. Surely I don't make any mistakes, right? Okay, you with me? Okay, now. There's another way of looking at this. And that is saying, okay, given that we know there is such a thing as the QR factorization, can we elegantly come up with an algorithm for computing it? Okay? And let me show you how that's done. I'm going to leave this up. It's starting to feel more like a computer science course, right? Now we have algorithms. This is good. I don't like thinking about individual elements. So we know that we have a matrix A for which we would like to compute a Q and an R. Okay? With the state of properties that I stated right there. Okay? What do we like to do in this class? We like to slice and dice. So the way I like to slice and dice this, remember, I only know how to count to 2. So I'm going to take A, I'm going to partition it into 3 parts. And I'm going to take Q, and I'm going to partition it into 3 parts. And then I'll take R, and I'll partition it into many parts. Okay? Where, remember, we have the convention that if we use a lowercase letter, then we know it's a vector, etc. So what these beasts are should be pretty obvious. And we're going to do this partitioning in such a way that this represents J columns, and a J by J matrix. Fair enough? Question?
The R sub 1, 2 transpose there?
Yeah. Why the transpose?
It's not really a transpose, right? It's just a to comment.
It's a label to demonstrate that it's a row. Exactly. Good. Okay. The other thing that you have to get used to in this class is partition matrix multiplication. Okay. Anytime I see this, what do I see? I see something that looks like this. And if I did this multiplication, I'd know exactly what to do, right? The output is a 1 by 3 matrix. And the way you would do it is you would do this times that plus this times 0 plus this times 0. The 0 matrix is sitting here. So that just gives us Q0, R0, 0. This times that plus this times that plus this times that gives us Q0 times R0, 1 plus Q1 times rho 1, 1. Here I'm just going to put a star. Some complex formula I don't care about. Okay? Why don't I care about it? Well, if you look at how the algorithm proceeds, the algorithm proceeds by taking the first j columns, computing an orthonormal basis for it, which gives you then this matrix R right here, right? So what we can say is we're done up to this point, where we know what those pieces are. And the purpose of the game is to now push ourselves forward by 1 column here, 1 column here, and 1 row and 1 column right there. Okay? Which means that here, we know what this is, we know what this is, we know what this is. But we also know that the j plus first column here is equal to the j plus first column here. Okay. So we know that A1 is equal to Q0, R0, 1 plus, and we can take the scalar and we can bring it out front, right? By the way, very important, this A1 here and Q1 here is not the same as the A1 here and Q1 here, right? Unfortunate part of the notation. That's why you should never think of it this way and only think of it that way, then you cannot get confused. All right? A1 here is the current column with which we're working. Q1 here is the current column with which we're working. Fair enough? So we've got this. And what we would like to do is we would like to compute this and this and this. And we only have one equation in 3 unknowns. But what do we know? We know that if we hit A1 on the left with Q0 Hermitian transpose, then that's the same as Q0 Hermitian Q0 R0 1 plus rho 1 1 Q0 Hermitian Q1. Well, what do we know? This here is the identity. And we know that all of the columns of Q0 are orthogonal to Q1, and therefore this is the 0 vector. And therefore we know that this is just equal to R01. So we have a method for computing R01. And notice that that's one matrix vector multiplied. Fair enough? Once we know what that is, we can say, oh, we can subtract this off of both sides. And what is that? That is A1 perpendicular. It's the component perpendicular to the columns of Q0. At which point we can then say, okay, A1 perp is equal to A1 minus Q0 times R01. That's a matrix vector multiply. And then finally we say rho 1 1 is equal to the length of that. And Q1 is equal to A1 perpendicular divided by rho 1, 1. Which notice is exactly what you have right there. Okay? Just derived in a different way. I can probably derive the same thing in at least 5 different ways yet. Okay? I'm pretty good at this, but I think that we've gotten the point. So then what we would like to do is we would like to say, okay, why don't we come up with a way of expressing the algorithm that nicely captures this? Okay, so what do we have here? We start by taking A and saying we'll have a left part of A and a right part of A. The left part are all the columns with which we're done. The right part are all the columns that we still need to work with. Same for Q, same for R. The important thing here is at the top of the loop we expose the next column in A and Q and the next row and column in R. And then we do exactly the updates that we just discussed. At that point, we're done a little bit farther. We move the thick line, which tells you where in the matrix you are forward. And you've got yourself an algorithm. Okay? Now, the problem obviously is that if you express it this way, and you then need to write an algorithm implementation for it, then you need to somehow take this and in your brain translate it back over to that, create all of these indices and loops and stuff like that. And there are all kinds of opportunities for creating bugs in your code here, right? So what we really want is a way of coding like this so that your implementation looks exactly like this. And let's take a break and let's do that. Okay, so we get out of this. The way we code, and I'll make a little exercise so you get some practice with this, is to why does Firefox decide to do this? Okay. So we have a website that we use to program. I'll put a link to this in there somewhere. We call this a Spark web page. Don't ask me why. And all you do is you fill out a form. We'll call it actually this is the classical Gram-Schmidt process. What we just did is an unblocked algorithm. An unblocked algorithm exposes a new column or row at a time, as opposed to several, and we'll talk about the importance of blocked algorithms later in the semester. We'll call this variant number 1, because we have to call it something. And then we generate, let's see, how many, let me see what we do here. Okay, so we have 3 operands. A, which we march through from left to right, and its input. We have a matrix B. Everything is always either input or input and output. So, sorry, we shouldn't call that B, we should call that Q, which we go through from left to right, and its input-output. And we have an R, which we march through from top left to bottom right, which is input and output. And what we've just done is on the right created a code skeleton in MATLAB's M script that corresponds to what the algorithm is there on the left. Okay? Probably should make this a bit bigger. You can sort of kind of see, you can stare at this a little bit, you can kind of see that there's some similarities there, right? And then all you do is you take this, you cut it and paste it into an editor. Let's see, we'll have to go to I don't have it set up somewhere. Okay. Yeah, I know. Let me just, let's see. We didn't want to go there. I think I have it in the house. I'll put it somewhere where we can also use it on Thursday. How's that? That way it sounds like maybe I actually did this on purpose, right? So we call this on very number1.m because it's an M script file. We put this in. And then all you're left with is having to cut and paste in the actual operations that are sitting right here into the middle of all of this. Okay, so you say R01 is equal to Q0 Hermitian times A1. A1 perp, we'll call it, is equal to A1 minus Q0 times R01. Row 11 is equal to, what is the MATLAB for length? Norm 2 of A1 A1 perp. Maybe it's norm 2. I'm guessing. Norm. I think that's good. Okay, and bingo, in theory, this is good. Now, how many of you believe that if you implemented the algorithm, any of the algorithms that I explained in something like MScript for MATLAB, or I use Octave, which is free, you would get the right answer the first time? Okay, willing to put $100 on it? Okay. All right, let's see if we get the right answer the first try. Okay, I need to put this here. Okay, just fixed my thing. So I'll start up Octave, and I happen to be in that directory, but notice that that file did not exist. Okay, there's nothing up my sleeves. I didn't cheat. Okay. What I'll do is I'll create a random matrix that's say 5 by 3. Now I need to create a matrix in which to put Q, so I'll create a matrix of zeros that's 5 by 3. And I'll create a matrix R that is 3 by 3. And what I'll do is I'll say the Q and the R that comes out of my Gram-Schmidt unblocked variant 1 of A, and then I need to feed in Q and R because I have to indicate how large those matrices are, okay? And we'll execute this, and it's undefined Y. I thought yeah, I did, okay. So unfortunately, I don't know how to go up. In MATLAB, I could just do the up arrow, but now I have to retype it. That's annoying. No? So it's not in this. Did I put it in the wrong directory? Oh, yeah, I put it in the wrong directory. Okay. Hold on. Gosh, I'm losing my $100 fast here. Huh. Yeah, it's not wise to bet against my programming, I tell you that. So I put this here, and I need to move the. Where the heck did I? Oh, codes. move that to house QR. That's actually the directory in which I happen to have my Octave session open. Now I should be able to double click on this, except that it didn't have the C there. Now it gives a whole bunch of error messages because the particular version, the routines that do the slicing and dicing of the vectors do so in a way that Octave apparently objects to, because it creates zero matrices, matrices of width 0, and I need to fix that a little bit. Apparently something is different, but the bottom line is that we got a matrix Q and a matrix R, so clearly I was right? Well, maybe, yeah.
So how do you verify that the transformation from the language to row to the upper is correct?
Oh, let's get to that in a minute. Let's first see if we just get the right answer, right? So we do an A minus, let's do format short so that we don't see so much. And then we do A minus Q times R. Notice that 10 to the minus 17 is fractionally 0, right? We don't expect to get the exact answer back. Ta-da! I mean, this is the equivalent of a magic show now, right? We've never seen this before. So your answer about all of the routines that we use being correct has to do with when we do this coding, we use and abuse those so much that if there were a bug in them, it would have shown up by now. The other thing to say is, look, those are just very simple indexing routines, so getting those right is pretty simple. Okay? We did not do a formal verification, but since you mentioned it, we can formally derive this algorithm and prove its correctness, and we can do that in the way that Dijkstra would want us to do it. Namely, we can do goal-oriented programming where we start by stating this. And from that, we derive the algorithm by deriving its proof of correctness. Ah! Nobody else can do that. So, since you're so interested in it, send me an email and I'll show you where we do that. Okay? Very computer sciencey. Too computer science. I'll give one lecture on this later on, but not now. There was another question, I believe. Ah, very, very good, because this is where Gram-Schmidt often fails. I think for a random matrix it'll do okay. Oops. Q prime times Q. Okay, for this one it does pretty well. But it's because we started with a random matrix. So we have reasonably orthonormal vectors that we started with. Okay, we're going to start running out of time if we don't watch it. Well, let's actually, since you mentioned it, let's skip around and let's go to the last. You always ask about the last section of the notes. So let's create a matrix that is going to give trouble. There is such a thing that's called the machine epsilon that we'll talk about more later on. If you've taken a numerical analysis course, you may have heard about this. What is it? It is the smallest element, smallest positive value. No, it's the largest positive value such that if you add it to 1, you get 1 back. Because of round off, obviously, right? Because mathematicians would say, well, that's 0. But, okay? Now, that tends to be on the order of 10 to the minus 16. So let's set our machine epsilon equal to 10 to the minus 16. And then let's create a value epsilon that is the square root of that. Okay? Which, when you're using double precision arithmetic, isn't a particularly small number. It's small, but it's not really small. Okay? And then we go and we create a matrix A that has as its columns 1, epsilon 0, 0, 0, epsilon 0, 0, 0, epsilon. Ooh, that looks nasty, right? But if we use format long and we print A, you notice that these are not actually zeros. You see that? I wonder what happened if we do a QR factorization of it. Let's go back up. I'm lazy, I don't like to type too much. I'll double click on that. Oop. Oh, now I need to have Q equal to zeros of 4, 3, and R I think is okay, right? So let's try it again. And we get that. Let's see what happens if we do A minus Q times R. Whoa, we're in great shape. That's better than I would ever expect. Let's look and see what happens if we check the mutual orthogonality of these columns. This should be the identity, right? We have values on the off diagonal. They're equal to a half. Van de Geijn loses his $100. Ah! No, we can't have that. Okay. So all the arithmetic wasn't double precision. Okay? Nasty. Okay? Now this is due to a phenomena that's known as catastrophic cancellation. If you took a numerical analysis course, you learned that taking large numbers and subtracting other large numbers off of them essentially destroys accuracy in those numbers. We'll get into details of this later on. But you know, if you have some large number, 1.00001, and then you subtract, I'll just talk about it. And you subtract something large off of it, you may lose a whole bunch of accuracy because you just took it off. Okay? Now think of what's happening in the Gram-Schmidt process. You take a vector and you start subtracting components in different directions off of it. So you know, the A perpendicular starts shrinking. What you end up with is a very short vector that if some error happened along the way when you were doing computations with the larger vectors, those errors may end up overwhelming the errors in what you're left with. Okay? And in particular, it destroys your orthogonality. The fact that you end up with very short vectors is okay, because what happens really is that the values in R over here are very, very small, and that's okay. Okay? But it destroys the orthogonality. Okay. So it turns out that there is a modification of the Gram-Schmidt process that fixes this. And since we're running low on time, what I'm going to do is I'm going to talk you through it and then let you read the notes. Okay? And I guess I'll talk you through it using the notes. All right. Let's go to full screen. Let's make this a little bigger. Focus on the thing on the top. What do we really have? We have a bunch of vectors, Q0, Q1, through, in that case, Qk minus 1. And we're given a new vector y, and what we would like to do is compute the perpendicular part to y. Okay? Now, one way of doing that is to say, take your y and subtract out the component in the direction of Q0, then take out y and subtract it. Okay, so you start by setting y perpendicular equal to y, and then you say take out the component in the direction of Q0, take out the component in the direction of Q1, and so forth. Okay? Now, in the process, Q perp starts shrinking, shrinking, and shrinking along the way. But notice in each of these computations, you continue to use the original vector y. And what happens is that these computations here end up with error in them. And it may very well be that this computation here creates error in the direction of the vector Q2. So now, this value here has some pollution in the direction of Q2, and relative to this computation, this may be small, but after you subtract off a whole bunch more, that error may become significant. And you never subtract it out, because you never say, take this polluted vector and subtract out all of the errors in the direction of Q2. No, you continue on. Okay? And the way to fix that is very simple. The way to fix that is to say, instead of subtracting out using the original vector y, subtract out using the updated vector that has been made perpendicular in the direction of all of these other vectors. Okay? And it turns out that you can easily prove that Qj Hermitian transpose y perp is always equal to Qj Hermitian y. And I go through that in the notes. Notice it's a trivial change. Okay? This is known as the modified Gram-Schmidt process. The disadvantage is that you can't cleanly compute all of these coefficients as one clean matrix vector multiply. You inherently have to do this in the loop, subtracting out the component one at a time, because you want to work with that newly updated vector. Okay? Except that there's a way of thinking about this slightly differently, which is as follows. Every time you compute a new vector that's now orthonormal to the previous vectors, take that vector and subtract the component in the direction of that vector out from all of the future vectors. Okay? And if you do that, and you read the notes very carefully, well, actually, how do I do that in the notes? I have a whole sequence of algorithms that slowly take you towards that. Let's see. Let's see if we can somehow get there in the 5 minutes we have left. What do we have up there? Notice that there, now, here what we're doing is we're overriding the original matrix A with the orthonormal columns, okay? So there's no longer a Q involved, and there's no longer, oh wait, no it is there, never mind, ignore what I just said. Okay, notice that at every stage, when we compute that coefficient, we now use AJ perpendicular as opposed to AJ. So that's how it differs from the Gram-Schmidt process that we started with. Going from the one on the left to the one on the right, all I'm saying there is, look, instead of creating a new matrix Q, let's just overwrite the original matrix A. And we don't need a vector AJ perp, because we can just take our vector AJ, we can subtract out the components in the direction of the other ones, etc. Okay? So we have that. Then going from there to here, what do we do? Here, we're saying, what if at the top of the loop, we've already subtracted out all of the components from the previous columns, somehow magically. Then all I need to do is take the current column of AJ, normalize it to be of length 1. And if I then take that, and I subtract that component out of all future vectors that I haven't touched yet, then by the time I get to those vectors, they will have had all of those components subtracted out, and therefore I'm at the top of the loop. I simply normalize it to be of length 1, and I move on. Okay? So that's what this algorithm does right here. Then this algorithm here says, oh, but instead of having one loop in which you compute the components, the coefficients, and then subtract them out, we can make that into 2 separate loops. So that you compute all of those coefficients up front. And then over here, I manipulate that. And in the end, it turns out that you can formulate this as a rank 1 update to the matrix. Now, rather than spending a lot of time on that, let me sort of show you in this notation what's going on. What's going on in this notation is that at the top of the loop, you've already computed this and overwritten A0 with the result of that. You've already computed R00, but you also computed all of these coefficients right here, because those are the coefficients used to subtract out components in the directions of the Q's that you'd already computed. Okay? What that means is that A1 now has already had a whole bunch of stuff subtracted out of it by the time you get there. And therefore, in the current iteration, what you do is you compute its length, and then these coefficients of what you need to subtract off of the future columns, which are then updated. And what it means is that your steady state is that all of this has already been computed, all of this has already been computed, and essentially all of these vectors have been updated consistently with them. What would we call that in computer science? That state has a special name. It's known as the loop invariant. Has anybody ever proven a program correct? Have you heard about the loop invariant? Okay, so this is what Dijkstra would use to prove the loop correct. Okay. And the neat thing is that if you then go one step further and you use Dijkstra's approach to goal area to programming, and you say, we can say what are reasonable loop invariants, so we can come up with the loop invariant a priori, and then that dictates what update must happen in the loop. So for those of you who are diehard computer scientists, this is Dijkstra at work. Which is kind of funny because Dijkstra despised numerical analysis. Okay? And it turns out that I believe we're the only ones who ever made his view of how to derive loops correctly practical. We, meaning my group, by the way. The rest of the numerical analysts haven't quite caught on to this yet. Ooh, I'm saying this on video. All right, so the important thing here is that there are these two different algorithms. And let's see what happens if you instead use the modified Gram-Schmidt. Now, notice that how you march through the matrix is identical in both algorithms. It's only the update that you make to the various parts of the matrix that change. So what we can do, this is actually what I just described here. And you're just going to have to go look at the notes and see what happens there. I will go back over here. I will put this into Gram-Schmidt unblocked. We'll call this variant number 2. We'll go ahead and fix the name of that. And when we now get down to this right here, notice that what we need to do is we need to still, okay, let's try to get this right next to here. We still need to compute the length. We still need to compute Q to be of length 1. So here I actually do compute Q. Then I'll compute R12 transpose as A1 Hermitian transpose times Q2. Oh, this is a problem. We have to overwrite A here. Hold on. Yeah, and so this should be A1. This should be A1, A1. And then this should be prime times A2. And then we need to take A2 and subtract simultaneously all of the components in the direction of the one that we just computed. Okay. Anybody going to bet against me? I guess what we should do here is we should take our A and back it up, so I'll put that in AA. I should take my Q and wipe it out, otherwise I might be cheating, right? Wait, no, because A is going to be overwritten, so it's okay. I should take my R and zero it out, right? Okay, and now should call, so now A is going to be overwritten with Q. Oh wait, I can actually do that this way, right? Because that's just the output variable. So I don't need to worry. Except that I might be cheating. Are you going to trust me not to be cheating here? I'll put in AA. How's that? Q is not going in, so I can't be cheating, right? Oh, okay. It's unfortunate that I now overwrote the previous Q, right? Oh well. Let's look at A minus Q times R this time. Now notice that that's interesting. My Q times R is not nearly as close to A as it used to be, huh? I wonder what happened there. But still, but let's look at how orthogonal Q is. Ah! I have an error! Ah! This is horrible. Huh? What's that?
Change it to the right return variable in the algorithm.
Let's have a look here. Let's see if we can figure it out. We put this next to... we're overtime. I could say we're saved by the bell, right? Okay, what did we do wrong? We computed the norm of A1. We then normalized A1 to be rho 1, 1. We then computed A1 transpose times A2. That should be fine. We then updated. That should all be fine. Oh. We shouldn't be returning Q, we should be returning A. Okay? That's what's wrong. There's hope. I thought it was a little weird that it wasn't computing the right thing. Okay, so let's now try again. A minus Q times R is now 0, and Q transpose times Q is now, well, still not perfect, right? And it turns out there are reasons for that. But much better. We noticed that previously this was 1/2. Okay, now this is 10 to the minus 17. So we're much better when it comes to the part. All right, so go read the notes. What this goes to show is that while mathematically modified Gram-Schmidt is identical to Gram-Schmidt, in the presence of round-off error, the subtle changes actually have an effect. Okay, and this is what this class is in part all about.